Let me recap what happened in the last lecture. So we considered the notion of push forward. So if you have some map phi between a pair of spaces x and y, then it reduces a map between the corresponding fundamental groups. Called push forward. Then we showed various nice properties of this map, in particular that it's the composition of push forwards is the same as a push forward composition. In particular, also that identity, push forward of identity, topological X, space X is identity homomorphism on its fundamental group. For example, if you have some sort of, if you have, for example, a retraction R from X subspace A, then the push forward of the corresponding inclusion map is injective. And we also showed that if phi map between from X to Y is a homotopy equivalence, then the corresponding push forward is an isomorphism. Between the fundamental groups. So this means that the fundamental groups of homotopy equivalent spaces are isomorphic. Okay. And then we finished by formulating a certain lemma needed to prove later one-Campion theorem. So let me remind you what was the lemma. We have some topological space X, which was covered by open sets A alpha, such they're all they themselves and all their pairwise intersections are path connected. And they all contain same point x0, the base point in our space, topological space X, in which we will consider loops. And then the statement was that any loop f x based base point x0 can be represented in a certain particular way, meaning that there exist loops H inside loops HI. I find a collection of loops HI which are whose image is entirely in some particular open set A alpha in X, such that our arbitrary loop F up to path homotopy can be represented as a composition of loops H1. So how do we show this? So F is continuous, and this means that for any point, so as F is mapped from an interval to X, for any point on interval, there exists its neighborhood Vs, and so without loss of generality, we will consider neighborhoods of the form just an open interval, intersection of an open interval with our interval from 0 to 1. Any neighborhood contains a neighborhood of this form, so for us it will be enough to consider such guys, and such that F of the closure of this interval well, I will possibly need to intersect it at 0 and 1. I mean, unless these points are already inside the interval, is so the image. This image belongs to of the closure of this neighborhood belongs to a particular open set in this cover for some alpha. Well, by definition of the continuous map, there exists an open neighborhood, right? But I can always, okay, first of all, I can always choose neighborhood of this form of an interval, and then I can always make it smaller to ensure that actually the closure of this interval also belongs to some particular A alpha, right? So this means that, like, okay, this is our interval 0, 1 on which we have F defined. So F maps, F is a map for X. Image of F looks something like this. And then we have some so X0 have some cover, so all X cover it in our A alphas, which looks something like this. Schematic picture, something like this, and so they all contain this point. And of course, if I consider a fixed point here, which okay, it belongs to one of the, since it's a cover, it belongs at least to one of these A alphas. And because of the continuity, I can always ensure, so if this is say f of s, I can also ensure that there is sufficiently small, well, open neighborhood of S, open interval of S, which so that its image is also contained inside this some particular A alpha. Where is this point f of S landed? And again, I can always actually make it, if I want, I can always make it as it's smaller that to ensure that actually closed. The image of the closed interval containing S is also entirely in this A alpha. I hope this is clear. Just the usual analysis. And then we do kind of an argument similar to what we already did before. We use the fact that this interval is compact space. And this means that actually there exists, so this, of course, all these neighborhoods, they give us some open cover. And since open cover of an interval, and since it's compact, there exists a finite subcover. By some of these VS's where this union is over, well, some particular set, some particular finite set. And again, similar to kind of to what we did already before, in I think in this proof of the homotopy lifting property, is that from this statement we can modify this statement a little bit to the following statement: that there exists a partition, finite partition of our interval, such that we choose the points as 0, or as 0 is equal to 0, then some next point S1 in this interval, S2, and so on till Sn, which is coincide with 1. So it's the points, ordered points inside the interval. So that such that for any I, if I consider an interval from Si to Si plus 1, this the image of this interval belongs to some again belongs to one of this, to one of the is completely in one of the open sets in our cover of X. Situation where our interval is split into smaller intervals with boundaries of these small intervals determined by SIs, so that each of these small intervals is mapped entirely into the image belongs to one of these capital A alpha subsets. And again, how can we, for example, go from this statement to this statement? Well, one kind of, well, it should be more or less obvious, but if you want to be concrete, for example, you can choose SIs to be boundaries of our intervals Vs, in this finite cover, right? If you had some sort of a finite cover by well, there was finite cover by open intervals, so that the closure of each of them satisfies this property. And of course, if you just take, for example, subdivision of our interval, which with endpoints of the interval coinciding with these boundaries, each of these smaller intervals will automatically also satisfy this property. And the property means the image is completely entirely in one of these A alphas here. Anyways, the idea again is just that we can, because of the compactness of the interval, we can split it into sufficiently small pieces. Because the compactness of the interval and continuity of our function, we can split it into some finite number of sufficiently small intervals, so that each interval is the image of each interval is entirely in one of these A alphas. Okay, and then what we want to do is essentially use this subdivision to define our factorization, which we will have here. So how does this go? So let me draw kind of another version of that picture. So it's more clear. Suppose our space X here, base point X0, and here is our path F. Which is an image of this interval, which we divided S1, S2, and so somewhere in between there, Si and S plus 1, and this small interval right here between image of this small interval somewhere here between image of f of Si and f of Si plus 1. Have the whole, in principle, the whole thing is divided respectively to this division. So this is f of 0, this is f of S1, then you have f of S2, and so on, till the same as f of 1, the same of f of Sn. Here you have, so, and penultimate point is f of Sn minus 1. let me also explicitly draw the previous point, the previous f, which follows before this is f of si minus 1. Sorry, this is just si minus 1. Preceding interval here. Okay, and we know that by construction, we know that, for example, this thing, this the image of this small interval which you have here is contained in one of these a's, and we also know that each a contains this point x0. Schematically, you have a alpha I, something like this, which contains this interval and this point. And similarly, for the previous interval, there is some other a which contains the base point and this, the image of this interval, the preceding one. This is a alpha I minus 1. And we know that by definition, by our condition in the formulation of the lemma, if you consider this intersection of any pair of the open sets in our cover of X, and in particular, if you consider intersection of this pair, a alpha I minus 1 and a alpha I, this is we know this is path connected, and we know that this contains each of them. We know that each of them contain our base point x0, so intersection also contains this base point. So we can choose this. It follows that there exists a path, since this is path connected, a path from which we let us denote it by G. Well, let me denote Gi minus 1. Gi minus 1 from x0 to f, this point f of Si, which also contains which also contained in this intersection, right? By construction. Point is a boundary both. This point is image of both this interval and this interval, and so it should belong to the intersection of this pair of A's, capital A's, and we can choose this such that this image of this path, the image of this path considered again as a function from an interval to x is contained entirely in this intersection. Right, since the intersection path connected, there exists a path I minus 1. And this can be done for any I. And now we will use this. So, okay, we consider this path and also consider the following path fi. So in words, we can define this fi be a part, which a path which is a part. So it's still a map from interval to x, which is a part of f, our big path f, which we started with from s I minus 1 to si. More explicitly, if you want to define it explicitly as a function, on the interval fi of s is equal to just this value is given by the value of f with certain rescaling and the shift argument. The point s equals 0 corresponds to si minus 1, and the point s equals 1 corresponds to si. This picture becomes a bit messy already, but this is, for example, this is essentially this part which I drew in this violet color is our f. This small path is fi, and this red orange path, small path, is fi1. And then we can see that, of course, by construction of these small passes fi, we know that, well, up to path homotopy, this f is given by composition of all these small passes f, i's, starting from f1 till fn. Well, I consider this up to path homotopy because I don't want to care about an order in which I compose this path. And then, as usual, we can, again, up to path homotopy, we can do some sort of insertion of trivial paths composed with as paths gi's and their inverses. Namely, here we can, well, let me, to make it clear, let me draw a kind of another version, a different version of this picture where only relevant things are shown. So we have the base point x0, we have a path f here, and then we have, for example, f1, piece f1 here, and then f2 here, f3 here, and so on. And from here we have g1. Here we have 2, 3, and so on. And finally, we have here last piece is fn, and we have a gn. Like this. Fn minus 1 here. So I can do the following. So I can insert here, I can insert gn bar between fn and fn minus 1. And so why this is valid thing, because well, if I go in the opposite direction, I have fn, gn, then I go back gn, and then I have fn minus 1. And then I continue in a similar manner. And okay, and it starts in the beginning, which is as usual we write on the right. I have in the beginning of this path, I have f1, and then G1 bar, 1, 2. So here I inserted a pair of G1 bar and G1. And I have similarly, I insert G2 bar, 2, then I have F3, and so on. So I insert these pairs of GI bar, GI, so that instead of just going this way, I go this way, then I return along G1 bar, and then I come back along G1, then I do F2, then I go along G2 bar, then go return along G2, F3, and so on. Okay. And then after this, after I did this, I can just say, okay, let me just use this expression which I have already here. So I can consider this pass, this piece in the composition, and say that this is Hn. So this would be a loop, because this is a loop based at x0. This, then for example, this pass, this part, F1 G1 bar, I define to be H1. So this is again a loop. Like this, F1 G1 bar, and this product G1 F2 G2 bar. This is will be my H2, which is a loop like this. G1 F2 G2 bar, and so on. I continue. So this will be my H1. This will be my H2. This will be my H3, and so on. And you can see that by construction, indeed, all of these HI, they are loops belonging to some particular AI, sorry, A alpha in this open cover. So how do we see this explicitly? Just by construction, the image of Fi this was inside A alpha. I minus 1. I hope I didn't. I did this change. Didn't mix up I and I plus 1. Let's see. So image GI So let's see. So GI here. Okay, let's look at this picture. So GI minus 1 belonged to this thing. Okay, good. So an image of image of GI let's check in the beginning. So as of okay, if we have 1, I equals 1, okay, and did it. It's probably easier to check with the notes. Okay, let's see. Should be correct. Oh, I see. Yeah, let me. What I want to do here. Yeah. Here it shouldn't be minus 1. Well, just a relabeling, but this will make things easier. Yeah, just relabeling. Because here, yeah, here, this thing I wrote in assumptions, this is GI. Because if, for example, when I equals 1, I equals 1, this should be, this should be pass between F1. When I equals 1, this is G1, this should be F1, and this should be F2, right? So this is correct. There should be, sorry, there should be minus 1 here. And okay, good. And this, again, this is just a redefinition of this G. And okay, then this is belongs to A. This also belongs to alpha I minus 1 because it belongs to this intersection. And we also know that image of G I minus 1 also belongs to the same thing, right? Because it belongs, if I change I to I minus 1 here, this belongs to alpha I minus 2 and alpha I minus 1. So in particular, it belongs to this thing. And so all this, and since from this you can see that all HIs, they also belong to this thing. Well, for general I, this HI is defined as G I bar F for I not 1 or not n. This is in particular this combination Fi Gi minus 1. And this is all of them belong to this A alpha I minus 1. This thing also belongs, the image of this Hi also belongs to this A alpha I minus 1. If you want this HI, it looks like this, right? It's a loop. like this in red here, because it first follows. Okay, this is hi plus 1. This follows first gi, then it follows fi plus 1, and then it returns along gi plus 1 bar. This is our loop, and it belongs, by construction, it belongs to one of these. So this is concludes the proof of the lemma. Are there any questions? Again, as I mentioned, this lemma can be used to will be used to show the one-cumbrance theorem, which is a very powerful tool to calculate fundamental groups. But already this lemma by itself, it already gives can be used to give some results. So let me consider some example. We use just this lemma by itself. Particularly can be used to show that the fundamental group of n-dimensional sphere, 1 for n greater than 1. So we know this is not for n equals 1. This cannot be true as a fundamental group because we know that this is non-trivial. We already showed that this is z. But for n greater than 1, this is trivial. And so how do we show this? Okay, first let me remind you the definition of this n-dimensional sphere. This can be understood as a subset of elements in n plus 1 dimensional Euclidean space. Consider it such that with condition that the sum squares of coordinates is 1. And then we can cover Sn by 2 open subsets such that A1 is Sn minus 0.1, 0, 0, 0, and A2 Sn minus point with coordinates minus 1, 0, 0, and so on. So for example, for n equals 2, this is just a 2-dimensional sphere, which you can visualize like this. And for A1, you remove north pole, and for A2 you remove south pole. And one can see that the intersection, of course, each of them are path connected. Because again, for example, by stereographic projection, you can show that they are all of them, they are just, both of them are homomorphic just to Rn. For example, by using stereographic projection. So they are all connected, and their intersection, which is so for one of them you remove 1 point on a sphere, and you get it's homomorphic to Rn. But if you remove if you consider intersection, this means that you remove a second point from them. And this means, in particular, this means that this intersection is homomorphic to Rn minus point, which is also, we know, is connected. It's connected when n. It's important here that n is greater than 1, because if n is 1, this is not connected. And we couldn't use this the statement of the lemma. So this is connected. This is path connected. And we can use we can use this lemma, and so that we can show that lemma tell us that any path, any loop in Sn can be is up to path homotopy is homotopic to a composition of loops in A1 and A2. But we know that AI are contractible. And this means that all loops AI are what is called null homotopic. Null homotopic, by definition, means that they are homotopic to a trivial loop, meaning constant loop. And since any loop in Sn can be decomposed into product of loops in A1 and A2, and this implies from the lemma we get that any loop in Sn is also null homotopic. And in particular, and then this means that pi1 of Sn is trivial. Any questions? So before we formulate von Kampen's theorem, we need to introduce some algebra definitions, which you may already encountered. But nevertheless, let me define this for completeness. So we want to define what is called free product of groups. Suppose we have a family of groups H alpha, labeled by some set I. Then we want to define a free product, which is denoted by this star. A star is kind of free product operation, and you take this free product operation over, you multiply all H alphas, and this index runs over our set I. So in particular, well, you can consider just free product when I is just a set of two elements. G can be, you can just write this is H1, H2. So first, we want to define this G free product as a set. As I said, it's a collection of what is called words or formal products of elements in our groups H alphas, meaning it's a sequences of elements, let's say a finite sequence of elements, G1, G2, Gm, and the sequence we just write kind of without any kind of additional signs usually. Just put one element after another, and such that so each GI belongs, it's an element of one of the H alphas, and we also want. If you do just this is a kind of what is called unreduced word, and so what we are defining here is actually what is can be called reduced words, and reduced meaning that we impose additional condition that if we have a pair of elements here with indices I and j, such that the difference is 1, so we have a pair of consecutive elements, something like gi and gi plus 1. This we should have that the corresponding alphas are different, meaning they belong to two different groups. For a pair of consecutive elements, they should belong to different H alphas. And this is what reduced means. Okay, this defines G as a set, but we want to define it as a group, and then multiplication between a pair of elements. The set, which can be chosen to be, for example, G1 from G1 to Gm, some finite sequence. And we want to define a multiplication of this finite sequence to another finite sequence. Let's say G1 prime, dot, G prime, let's say M prime. And what we want to do, we want, okay, let me write the following. So what you want to do, you want just consider a sequence of elements by just concatenating these two sequences. So you first follow this sequence, and then you continue with this sequence. G1 prime, M prime. But this is not in general what you want. What you want to do, we want to consider this sequence, and then you want to reduce. So this would give you, in general, not a reduced word. This give you just some sequence. This condition might be not satisfied. What you want to reduce it according to the rules, the following rules. Well, let me write, okay, there is no place here. Let me write these rules star and 2 star. The rule star is that if you have anywhere in the sequence identity belonging to some H alpha, so each element of the sequence is belong to some H alpha, we want to remove this, just remove this element in the sequence. And the second rule is that if you have a pair, consecutive pair of A and B elements, so this is considered as 2 symbols independent. So this is element of H alpha, and suppose the next element also belongs to H alpha for the same index alpha. In this reduced condition, there also that this GI in the reduced word, this GI is not identity, cannot be identity. Okay, so the second rule is that, okay, if you have some element in H alpha and the second element is also in H alpha, then we replace this subsequence of 2 elements to a single element, which is a product, which is a result of multiplication of A and B in H alpha. This reduces both these rules. They reduce the number of symbols in your word by 1, and it's easy to see that any unreduced word for which this condition and this condition just is not necessarily satisfied. So it's just an arbitrary sequence of elements of our groups. By applying these 2 rules, we can always bring it to a reduced word by a finite number of steps. Of course, okay, we kind of define this multiplication, but in principle, we have to check that it actually satisfies group axioms. The remark is that it satisfies group axioms. So the first group axiom we have to check is that existence of identity. So identity in G, which is a neutral element, and this is just given by empty word. In this sequence, the sequence is allowed to be empty. So m equals 0 is okay. And of course, by definition of simplification, if you concatenate one word with an empty word, it doesn't change. So identity is the empty word is indeed a neutral element. And second axiom is existence of inverse. And we want to consider inverse of some arbitrary sequence of some arbitrary reduced word. Easy to see that the role of inverse is can be given by taking the sequence of inverses in the opposite order. Indeed inverse, because if you can see that if you concatenate this word inside the brackets with this one, okay, you get well, let me write it. Maybe it's pedagogical to write explicitly. So if you want to check that if you multiply it, this thing to this one, so by construction you have to concatenate these two words first. And then you should apply your rules, star and double star, until you get a reduced word. How does this go here? So here, okay, we see here we see a sequence. So both elements, they belong to the same. They necessarily belong to the same H alpha for some alpha. So we can apply the rule double star to do this multiplication, but the result of this multiplication, so here it will be identity in H alpha. And then I apply a rule star to just remove it. So application, if application of first this rule and this rule gives me G1, G2, blah, 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 Gm-1, Gm-1 inverse, and so on, G1 inverse. And then I do it again and again, and I finally arrive at an empty word. The identity in our G. Okay, and finally we want to check associativity. And this is, well, this is basically, again, some play with these words and applying these rules. And it should be more or less obvious that this should hold. But to do this explicitly, I leave it as an exercise. If you have any problems, let me know. Okay. So now, okay, maybe it's instructive to give some example, not so abstract. Suppose we have a G, so we want to consider G, which is a pre-product of a pair H1 and H2, where H1 is a copy of a cyclic group with two elements. Suppose this is generated by so you can understand that H1 is generated by some A, and you have a relation that A squared is 1. And similarly, H2, which is also isomorphic to, it's a copy of a cyclic group of these two elements. But to distinguish them, let me denote the generator here as B, which also squares to 1. The two copies, essentially, of the same group. And so what is what is G? So G, you want to consider all possible reduced words. The words of the form follows. So you can suppose you can start. Well, you always have to start with something, unless it's an empty word. So you start with, say, with A. So and what can you write next? Okay, this by definition. So yeah, this has only two elements, non-trivial elements: identity and A. Okay, you're not for reduced word. You're not allowed to insert identities, but you can start with A, right? And then the next element, so since the word is reduced, should be an element in H2. And the only non-trivial element in H2 is B. Then the next word should be not in H2, not element not in H2, but in H1, because it's reduced. And so on. You continue. The only thing you can do in this case is just alternate them until you stop somewhere. Well, the other possibility is you start with B and do the same thing. Well, this is fine. As the dot means it actually stops somewhere. How do you do multiplication? Suppose suppose you want to multiply element ABA, for example, to itself. Or maybe not. Let's say multiply ABA to AB. And okay, so first you kind of concatenate these things, and then you want to reduce it according to our rules. Okay, here you have two consecutive elements from the same group, so you can replace them by one element, which is a product, and the product here is identity, and you apply another rule which tells you can replace an. So this becomes this. Then first you can reduce this B, and you end up at A, which is reduced. So in other words, so another way to understand this free product is that suppose you have start with groups which have some defined in terms of some generators and relations like this. And the free product is just a group for which the generators is a union of generators and the relations are union of relations. And you don't add any additional relations. And well, maybe it's instructive to see that this free product is not the same, is not isomorphic the usual product. The usual product, which is usually done by this, and this would be just this group. The direct product would be a group of four, just has 4 elements. Right, it's just pairs like this: 1, 1, 1A, sorry, A1, H1, this is H2, and 1B and AB. So you have here you have these pairs and nothing more. And by in construct here, there you can see that there are infinite number of elements in the free product. Here we have just 4. So there is a big difference between the usual product and the free product. Here you can understand, okay, in a sense, you can also write all elements. You can understand this product as also a group generated by just A and B, so that this is just 1, this is A, and this is B, and this is AB. but you have a condition, you have a relation a squared equals 1, you have a relation b squared equals 1, but you also have a relation that ab is the same as ba. We don't get anything new apart from this. So the difference from this point of view and the free product is also can be generated by the same guys, but the only relations are relations inherited from individual groups, and there is nothing else. But here you have additional relation where these two guys commute. Any questions about the free product of groups?
Yes, I have a question.
Yes.
In the definition of the free product, I don't see us using the fact that the absolute value of the difference between I and J should be 1.
Sorry, can you speak up a little bit? I couldn't hear.
Okay, the example we just treated using Z2, I don't see us using the fact stated in the definition of the free product that the absolute value of the difference between I and J should be 1. I don't see how it applies.
Sorry, the question about what is this?
Yes, the definition of the free product. Not the example, the definition of free product.
Oh, this thing?
Yes.
Oh, okay. Okay, let me explain a little bit more. So well, this is just kind of shorthand. So what is this is just kind of a compact way to state the following: that if you have somewhere in this word, you have a gi plus 1. They should belong. Suppose this belongs to some h alpha I, and this belongs to some h alpha I plus 1. So these two things, these indices should be different. They shouldn't be the same. Well, this is the same condition because the I minus j absolute value equals 1 is equivalent that j is equals either I plus 1 or j is equal to I minus 1, right? And this means that j and I are differ by 1. And this is essentially that yeah, this is the pair of j and I. So here, this pair yeah. So you see, for example, if this is if I use this condition, alpha I is not equal to alpha j, is exactly this condition. And well, in the case of this thing, I just relabel I and j. I change I and j. Yeah, this just means that I and j is differ by 1. So there, these are two. You have this means that you have either gi, gj consecutive elements, or you have j, gi consecutive elements. Because either j is I plus 1 or j is I minus 1. Then you have this situation. And the corresponding groups should be different. Meaning, which is equivalent saying that these indices which label them, they should be different.
Okay, thank you.
Any other questions? Well, another definition which will be useful for us is the following. Again, definition of free product. I can call free product of not groups as we had before, but free products of homomorphisms between groups. Suppose you have homomorphisms phi alpha from H alpha to some group K. So we have a family of groups again as before H alpha, and for each of them we have a homomorphism, group homomorphism to another group K, and then the free product of these homomorphisms, which can be also denoted by this star, will be a homomorphism from free products of our H alphas, this K, so that, okay, how do, and it's defined as follows. So an element here can be represented by, again, some reduced word, the sequence of elements, each of which belongs to some of these H alpha. So this, for example, this belongs to H alpha 1, G2 belongs to H alpha 2, and this belongs to H alpha m. And again, in principle, we want to also say that this is reduced, meaning again, for two consecutive elements, they belong necessarily to different groups, and there is no identity here, and the identity element of some of the groups. And this, so this gives an arbitrary element in the free product by definition, and we want to map it to the following. So we just take the following product, the product in K, so K is a group of images of individual elements in this word. So here again, this is kind of, here we had some formal product or word, so kind of formal sequence of elements. But here the results of the application of the maps phi alpha, they are actually they are multiplied using the group structure in K. And it's easy to see that this is indeed a homomorphism. It's easy to see that because, well, just by definition of the product here, if I take a pair of elements here, take a pair of words, what I have to do, I have to concatenate them to get a product. But if I concatenate them and then this is equivalent, and I have to compare this with the result of application of this phi. But we know that the concatenation here will correspond to just indeed will correspond to multiplication of the result of phi. And of course, since all individual phi alphas were homomorphisms, this respects these rules, right? Again, I'm not showing this explicitly, but in very detail. But again, this should be pretty obvious. And if you want, you can. Not clear, you can ask me. Okay. Okay, let me now we are ready to formulate one-compens theorem, and so I'll just formulate this, and then we'll prove it next time. Well, before, let me fix some notations. So let me assume the conditions of the lemma that we had before. In the conditions of the lemma, remind you, so we have an open cover X, an open cover like alphas, which satisfies some particular conditions. So in particular, they all were path connected, they all contain base point of X, and they are all interpairwise intersection were path connected. And let me denote I alpha to be a canonical inclusion map from A alpha to X, and A alpha beta be an inclusion of the intersection to X. And then let me denote by G alpha. This is just to kind of to make things more compact. They push forward of I alpha. So this will be a map from pi 1 A alpha X0 to pi 1 X X0. And similarly, J alpha beta will be a push forward of this inclusion. The map from pi 1 A alpha intersected is L beta X0 to the same pi 1 of X. So this is just a notation. Then we formulate the one-compens theorem. Again, we assume the conditions of the lemma, and the first part is that if you consider phi, which is the free product of homomorphisms J alpha, this is surjective. And the second part, so this free product is a map from free product of this pi 1 of A alphas to pi 1 of X. And the second part is that if we impose additional assumptions that all triple intersections are path connected, then the kernel of phi the normal subgroup of this free product of pi 1 of A alphas. And moreover, it's explicit. It has explicit description. It's generated by the following elements of this form: G alpha beta of omega multiplied by G inverse, or G multiplied by G alpha, G beta alpha of omega inverse, where omega is runs over all elements of pi 1 of the intersection and for all possible pairs. alpha beta. And this in particular will imply, since this kernel is a normal subgroup with particular, this will apply that that pi1 of x is isomorphic to this free product of pi1 of A alpha divided by this kernel. Just by the main theorem in the group theory. Okay, well, I will recall this formulation in the beginning of the next lecture. But yeah, for today I want to finish. But if there are any questions, let me know. Yeah, I will start next lecture by repeating this thing and making a few comments. But yeah, the idea is that this, in particular, will give us an explicit way to calculate x by considering its open cover satisfying some properties. So we have explicit description of this. If we have explicit description of pi1 of this open sets, and we also, the theorem gives us explicit description.
Hello, sir.
Yes. Is there a question?
Hello. I want to ask if knowing whether the kernel is trivial or not is something complicated. Like, are the condition for it to be trivial? Is that something complicated?
Well, I don't. Well, the condition is just this: all things are trivial, right? I don't know. It's in general, this is what it is. If these things, if this element is always the same as this element, if you can show that, then it's trivial. But otherwise, it depends on situation. Yeah, just. I mean, this gives you this gives you the way to verify this statement explicitly.
Okay, thanks.
Basically, this means that actually I was. I think I was.
What if the intersection between any A alpha and A beta had the trivial fundamental group? Would that imply that the Kerr is trivial?
Yes. Yeah, because omega would be trivial, and this is a homomorphism. Yeah, this would imply. Yeah, of course, in this case, this would be automatic. Sorry, I was a bit in a hurry, so actually might. Well, again, I will repeat this in the next lecture. So this was actually an inclusion, not in X. This was an inclusion in A alpha, and this was mapped to not pi1 of X, but pi1 of alpha. Kind of partial inclusion. Otherwise, it's kind of trivial because otherwise this would be identical. These J's would be identical maps. But here, the order of alpha and beta is, of course, important. Any other question? Okay, if not, we will resume on Monday.
Okay, thank you.
Thank you.